Hello everyone, this is Taylor and he will be talking to us about the diesel cycle.
Hey guys, I'm Taylor and I'm here to talk about the diesel cycle. Before I talk about the diesel cycle though, I'm going to remind you guys what a power system is. And a power system is just basically a cycle of processes that bring you back to the initial phase of the whole cycle. And each phase has its own thermodynamic characteristics, and each process is done by having the fluid travel through a mechanical device like a compressor or a heat exchanger. Now the diesel cycle works by work coming out of the heat exchanger from the diesel being combusted. And it's very similar to your car engine, which is a 4-stroke internal combustion engine. The way that it's different though is that diesel is injected at the point of the most compression, as opposed to having a fuel and air mixture. And it also has a spark plug. Now, the thermodynamics of an internal combustion engine is using the first law and assuming that the process is reversible and steady state. And that results in the steady flow energy equation. And this equation is very similar to the Euler equation used in fluids that you guys are aware of. So to get the work out of the process of combusting the diesel, we assume adiabatic and that kinetic and potential energy is neglected. So then we get work is the difference between the pressure over the density of each state. And here's an animation to show what it looks like. So there's 4 strokes that happen. As the piston goes down, you have an intake of air. As the piston goes up, it compresses that air. And at the point of most compression, you inject the diesel, which is how the explosion happens. As the explosion happens, it pushes the piston back down, which is how you get the power out of each cylinder. Which is why most car engines have at least 4 cylinders, so that since the whole cycle is 4 strokes and only 1 stroke produces power, that's why you need at least 4 cylinders, so that you can get power at all times. And the last stroke is to eject the emissions. Here's the processes on the PV diagram. The first process is from state 1 to 2, which is the compression of air. State 2 to 3 is the instantaneous combustion of the diesel, which produces heat. And that's assumed to be reversible and at constant pressure, since we're looking at a instantaneous process. And from 3 to 4, we assume isentropic for the expansion of the energy released after the explosion. So there's that. And from 4 back to 1 is the ejection, which is the exhaust. And we assume that to be reversible. The first process is the intake, which is not on here. It doesn't have thermodynamics involved. It's really just purely mechanical. There's negative pressure, which happens from the weight of the piston along with the momentum of the last stroke. So that's how that happens. The compression happens by the crankshaft putting energy into the system. So you have to put the work in order to compress the air to get work out. And here is the work when you simplify the steady state energy equation, this is how you get the work. And we also assume isotropic. State 2 to 3 is the combustion. Like I said, it's reversible in constant pressure. And this is how we get the heat out of the same equation. There is some work involved with this, but it's mostly negligible. State 3 to 4 would be the power stroke, which is resulting from the explosion. This is how we get the work out, same as before with the compression, just in reverse. We also assume isotropic, so no heat involved there. And last, the exhaust stroke. Same as the, you calculate the heat the same way you calculate from the combustion phase. The efficiency is calculated by having the heat subtracted, so you have QH minus QL. I forgot to put that up there, but both sides are divided by QH. And that results in this final equation, which has the pressure ratio and the volume ratio, which are characteristics of the engine itself. And diesel engines are normally used in power generation, automotive, and aerospace applications.